Hello, Arjun sir. Am I audible?
Yes, madam. Yes, madam. It's audible.
Okay, thank you, sir. Yeah.
Praveen, sir.
Yes, sir. Yes,
Yes,
sir.
yes.
Can we start? Can we start?
Yes, sir.
Sir, 1 second, 1 second. Wait for 2 minutes. The participants are joining now.
Sure,
One
sure,
second,
sir.
1 second, 2 minutes.
Sure,
Okay,
sir.
okay, sir. Hmm.
Okay, sir. Shall we start?
Yes, sir. Yes, sir.
Okay. Ma'am, Anjana ma'am, please.
Okay, sir. Thank you. Good evening, everyone. Welcome to the day 4 of our session. It's my pleasure to introduce our esteemed resource person for the day, Dr. A. Hemachandar. Dr. A. Hemachandar earned his PhD from NIT Raipur and is currently serving as assistant professor in the Department of Electrical and Electronics Engineering in NIT Puducherry. Prior to this, he worked as an assistant professor at Gayatri Vidya Parishad College of Engineering for Women, Visakhapatnam. With an impressive portfolio of 16 journal publications, including 3 in IEEE transactions, 25 conference papers, 6 book chapters, and 4 filed patents, Dr. A. Hemachandar is a prolific contributor to his field. His expertise lies in power electronics, focusing on renewable energy and EV applications. He is working on a significant project funded by the Ministry of Electronics and Information Technology, Government of India, worth rupees 30.53 lakhs, titled Design and Development of High Power Density Wide Bandgap Devices Based DC-DC Converters for Two-Wheeler, Three-Wheeler EV Applications. In addition to his research, he serves as a convener for the institution's Innovation Council at NIT Puducherry, furthering innovation and entrepreneurship. Please join me in welcoming Dr. Hemachandar, sir, and let's take this opportunity to an insightful session. Over to you, sir. Thank you.
Thank you, ma'am, for the wonderful introduction. Thank you for giving me this opportunity, Praveen sir. So I think for the time being, I will just switch off my camera so that I'll have some good bandwidth. In the remaining, after the presentation, again, I'll share it with the, I'll start my camera. So good evening all. So today's topic for discussion is multi-port converters for sustainable energy conversion. What is multi-port? Why do we go with multi-port and why this sustainable energy has come? See, this is all what we'll be dealing with. And if time permits, we'll go with how to create one multi-port converter. If not, we'll see with some sort of how these multi-port converters are actually helping in sustainable energy conversion. So even before this, coming to this sustainable energy, mostly we'll be using all the DC-DC converters. These are all the conventional DC-DC converters, the buck converter, boost converter, and the buck boost converter. So not more on this. So where do you use this DC-DC converters? You use it in every application. These DC-DC converters are widely used, mainly in the photovoltaic application. If you see, it is used for achieving the MPPT. Now, again, when I call about MPPT, what is MPPT? So it is simple maximum PowerPoint tracking. It goes something like that. But why? What is exactly this? So, if you like to understand that, that is really a very wonderful, concept. Basic concept, but very wonderful concept. So here, if you see, this is your PV curve, and we always try to achieve this part. So why do we wanted to achieve that point? That is the maximum power point. Why do we want to do that? So the very simple reason is, say in case if you have some maid in your home, you always ask her to see that is not clean, this is not clean, you need to clean this properly, you need to clean the utensil properly. This is what we tell. But what is the amount you are paying to maid? It is hardly 1,500 to 2,000. Now, when you come to this photovoltaic applications, you invest some crores of rupees and you cannot let the energy get wasted like that. So when and wherever possible, we need to try that we extract maximum from it. So that is the reason why we always stress or emphasis on this MPPT converters or MPPT. Now, what is that we are doing? We are trying to use this DC-DC converter for this one, for achieving MPPT. So there are different techniques, MPPT techniques. Anyway, I'm not focusing on them because these might have already been known to you. So this is a basic P&O algorithm, perturb and observe algorithm, where you keep on checking the power with the old power, and then you'll be perturbing the power, and they will be slowly increasing the duty cycle. So here if you see similar to a maximum power transfer theorem, where you always need to achieve the source resistance and the load resistance to be equal for maximum power transfer. That is what our maximum power transfer theorem tells. The Thevenin equivalent should be equal to the load resistance. So the same thing is what we are trying to do. So if you consider with respect to the MPPT, that is sorry, with the respect to the PV panel, the boost converter and the load resistance together will form the load. So this is the source, and then boost converter and load resistance together is the source. Sorry, load. Now, how do we achieve this? It is not possible simply by converting or taking some random equations, or you cannot say RT must be equal to R0. So, in case even if you say RT is fixed, why? Because RT is the input resistance. That input resistance is VMP by IMP. And if you consider R0, it is also fixed. The load is fixed, or it may vary suddenly. But because of there is a variation in load, I cannot say I will not achieve MPP. No, that is not possible. So what we try to do is we try to have one small converter, which you call it as a boost converter. And this boost converter is responsible to achieve MPPT. How? By varying something called this duty cycle. So how do you do this? It is very simple here. You know, if you consider this V0, you can write it as V0 equal to V in, V0 equal to V in by 1 minus D, and I0 equal to I in into 1 minus D. So I wanted the powers to be maximum. So whatever the input is there, I wanted it to be the output power. So if I do and convert it with respect to resistances, it will be like RT equal to R0 into 1 minus D whole square. So here, if I wanted to make the load resistance equal to Thevenin resistance or the input resistance, I need to vary the duty ratio. And the P and O method or whatever the MPPT method you have used, that will help you in varying the duty ratio. So this is a graph where you can see that this is the load resistance line or load admittance line at D equal to 0. And this is the load admittance line at D equal to 1. So if your load line, that is if the value of your load admittance lies in this range, then only you can achieve MPPT using a boost converter. Similarly, in a buck converter, you can achieve MPPT only in this range. So this is why we are trying to use a boost converter to match the impedances. So what we are trying to do is we are trying to actually match the impedances, the source impedance and the load impedance, so as to transfer maximum power from the source to the load. Now, in case if I have a general system, it will be something like this. So I have multiple sources, I have multiple DC-DC converters which are connected to a DC bus. So this is, say the first one is your PV system, wind system, battery, fuel cell system, battery system. Each will be connected to its own DC-DC converter. So this will help in achieving MPPT of this. This will help in achieving MPPT of this, and so on. Similarly, on the other side, so this is all connected to a common DC bus. On the other side, we have a DC-DC converter, which will supply to the DC load. So again, it will step down its voltage and it will give to the DC loads according to the required voltage. And the same, we have one more connection which will be giving to the AC loads through inverter and transformer. Now, there are few problems with this conventional arrangement. So the first and foremost is that when I go with, you see here, there are 4 sources. So we have 4 converters. So when there are 4 sources and 4 converters, now I talk about let's suppose that all converters are boost converters. Now when all the 4 converters are boost converters, I need 4 boost converters, which I mean I need 4 switches, I need 4 diodes, I need 4 capacitors, I need 4 inductors. So all the components, the number of components that you are using is increased 4 times. Similarly, now I have a switch. So when I talk about a switch, each switch is having 2 states. One is on state, one is off state. So when it is in on state, there is some conduction loss. When it is switching from on state to off state, there is some switching loss. So when this switch turns on, turns on, off, there will be some power loss across the switches. So when the number of switches are more, it is obvious that the number of the total loss is more. So because of using 4 different converters, I have 2 disadvantages. The first one is the number of components is increased. Because of the number of increase in the number of components, the number of the cost of the system is increased and the weight of the system is increased. Apart from this, I am increasing the losses, which means I am having a reduced efficiency. So this system has this problem. So what we plan to do is we plan to eliminate this system somehow. That is what we'll see how. So what we are trying to do is we are trying to use something called as a multi-port converter. Now, what exactly this multi-port converter is? So this multi-port converter is one which is having more number of inputs and more number of outputs, or one or more input and a single output, one input, 2 or more outputs, 2 or more inputs, 2 or more outputs. So these are various combinations of this multi-port converters. So why or what are the advantages of doing so? So the advantage of doing that is you can integrate all the different sources. And when I call about a different source, all the sources need not have a similar characteristics. So I'm able to integrate all the different types of sources which are having different characteristics. And also it is capable of generating different output levels if required simultaneously. So because of this multi-port converter, what we are trying to achieve is instead of 4 different converters, I'm using a multi-input converter. So instead of saying multi-port, I'm going with multi-input converter. So because there are different inputs, and I'm having the output will be as per the requirement of the DC loads, and I will have one more inverter, and I will have a transformer and connect it to the AC loads. So now, how many switches do you have? That depends on your topology, but surely the number of switches will decrease. And another important advantage is you need not use 4 inductors. At least you can reduce the total number of inductors by 2. So you will use only 2 inductors. Maybe you need 4 switches, but the number of inductors is reduced, which improves the system, which decreases the cost of the system, which also decreases the weight of the system. So why do we use multi-port converters? So when there are, especially when there are different sources, we cannot have, I mean, when there is a huge demand in the load, we need to go with multiple sources. So when you are integrating these multiple sources, instead of using these DC-DC single converters, you go with multi-port converter, which has the advantage of lesser number of component count and higher efficiency, less cost and less weight. Apart from this, we also have one more advantage, that is when you have 4 converters, you need to control each and every converter separately. So instead of controlling each and every converter separately, if I have a multi-port converter, control aspects, the control complexity will be reduced. So what are the key features? The features include the structures are very simple and modular. Modular, you can, like, whenever you feel like add an extra source or remove the extra source, you can do that. The independent control of sources is possible. So in case if you want source 1 to act, you can go with only source 1, source 2, 3 can be off, and vice versa. So the flexible control structure with higher degree of freedom is possible. Individual and simultaneous operation of sources, compact and simple design. You can integrate with different sources, reduced component count and improved efficiency and reliability. Apart from that, the advantage is coordinated control, which is possible through this multi-input or multiple port converter. So these DC-DC converters generally are classified as based on the inputs and outputs, number of inputs and outputs. They can be classified as SISO, single input, single output, multiple input, single output, single input, multiple output, and multiple input, multiple output. Leaving the first one, all the next three can be classified as a multi-port converters. The only variation is in the either input or output or both. So now if you would like to classify these multi-port converters again. So the further classification of multi-port converters involves or is based on the first one is isolation requirements, number of outputs, operating direction, type of connection, gain factor, and structure. So in case if the converter is having or you require some isolation. What is isolation? Isolation is nothing but separation between the input and output. So like in case if it is a grid connected system, most of the cases if you go with a grid connected system, unless and until you follow certain standards, you require isolation. Or if you consider this electric vehicle charging stations, you require isolation. So based on the separation of input and output terminals, you can classify the system as isolated and converter as isolated and non-isolated converters. If you have a single output, you can call it as a single output system or a multiple output system. The same is valid for inputs also. So in case if you are using some energy storage devices like supercapacitors or batteries, in that case, you need a bidirectional. So multi-port converter can also provide you with either unidirectional capability or bidirectional capability, of course, based on your design. You can connect all the sources or loads in series or in parallel. You can have a very high gain or a very low gain. Similarly, you can have a modular or a non-modular structure. As I was telling you, modular structure means in case if you are interested to improve something or add one more source to your system. If the structure is modular, you need not completely disturb the system. You can add within no time and with less effort. If the system is non-modular, it is not possible for you to add it. So I think so what are the different applications of multi-port converters? So these are the different applications of multi-port converters. So if you see with respect to mostly it is with respect to transportation and solar and hybrid systems. So in case if you are using with electric vehicle, now when you have going with electric vehicle, if you have a bike, you have some battery of 48 volts, something like that. But some parts of the 48 volts or 72 volts, whatever you are providing, it is required for the motor to drive. So motor will require that you are giving that. At the same time, you also have some auxiliary parts in your vehicle. For example, your headlamp, your tail lamp, signal indicators, what you call wipers, etc. So in that case, you need only 12 volt or maximum 14 volt supply, 13.5 to 14 volt supply. So in that case, you need this multi-port converter to convert this 48 volts should be converted to 48 volts or 70 volts as per the battery requirement. Along with that, you also need to convert this 48 volt into 12 to 14 volt, which is required for the auxiliary parts. So in that case, you can use this electric vehicle and use this in electric vehicle. If you consider this hybrid electric vehicle. So in hybrid electric vehicle, in case if you have two or more sources, suppose the battery and the supercapacitor are there, in that case, you need to have a proper power management between the two. In that case, you can go with this multi-port converters. Similarly, you can connect, you will have it to standalone solar systems or grid connected solar systems, household systems, and many. So, since this is more related to this sustainable energy, we'll be more emphasizing on photovoltaic applications. So again, in photovoltaic applications, you see various issues in photovoltaic systems which can be addressed. For example, you wanted to improve the efficiency, or you wanted to improve the efficiency of the overall plant or the solar panel, and there are many. However, it is not possible for us to cover everything. I have taken one particular issue, which we call it as partial shading. So, what is this partial shading? For example, there are a number of panels at one point. Of all the panels, if there is some shading between or among few panels, and the remaining panels are not at all affected by any shading, in that case, the panel has two different shading levels or irradiance levels. Some part it is shaded, and the remaining part it is not shaded at all. So those kind of cases we call them as partial shading. So when it is in partial shading conditions, there are some effects on the solar panel. So the first and foremost effect is it causes, what happens is there is a chance that it goes with something like what do you call it, hotspots. So there will be hotspot from the particular point will be like cannot dissipate, or particular cell cannot generate any electricity. So that is what you call formation of hotspot, or the module performance will be deteriorated, efficiency will be reduced, and then if you work in the same partial shading condition for a longer time, you may have the degradation of the module also. But what exactly or how do you get this partial shading? So there are majorly two types of partial shading. One is called static and the other is called dynamic. Static means it stays for a longer duration. Dynamic, it quickly changes the weather. The shading condition quickly changes. For example, uh, today I have installed one complete solar plant, say on my rooftop. So nearby there are no buildings, so it is all good. But maybe in the near future, maybe after 1 year or 2 years, my side house, my house, adjacent to my house, they have started constructing a big building, which is taller than my house. So what happens? The shade of the building will be falling on my solar panel for a very longer time. So that is what you call it as a static shading. And maybe trees, tall buildings, passing clouds. When this passing clouds, when it is sunny, fine. Suddenly, cloud comes, and again within no time, the cloud passes away. The irradiance will be again to the maximum level, or there is no shading. That we call it as dynamic shading. So, what are the major limitations of the conventional systems? That is what the small depiction. So, suppose that there are four panels where two are connected in series, these two are connected in series, these two connected in series, these two connected in series, and finally this combination is connected in parallel. So when it is like this, I suppose that each and every panel is having 50 volt VMP, IMP is 5 ampere, 250 watt at STC, 250 watt peak power at STC. STC is the standard test condition. So when we have this kind of environment, now what we are trying to do is we are trying to assess the performance of this during partial shading. Now, suppose that there is a partial shading. Now, when I call a partial shading, you see here, the complete panel is not shaded. Only small portion of the panel is shaded because of cloud, some disturbance, whatever you call. So what happens exactly in this case is, each panel should come or should give you 250 watt, 50 volt and 5 ampere. This panel will give you 50 volt and 5 ampere because there is no partial shading. These two also will give you 50 volt 5 ampere because there is no partial shading. However, if you see this, because of the shading effect, Here you cannot get 50 volt and 5 ampere, that is 250 watt. So the reason being the shade. Suppose that it is just an example. Suppose that here what is happening? I am getting only 45 volts at 3.5 ampere. So the total power is only 157 watt because of shading. That is fine. Now, when I call something like KCL, Kirchhoff's current law. Here 5 amperes current is flowing. Here 3.5 amperes of current is flowing. Kirchhoff's current law does not or is not valid here. Why? Because these are in series. There are two different currents flowing, which violates KCL. So this circuit is this cannot happen. Now what should happen? This anywhere cannot give 5 ampere, but this can give you 3.5 ampere. So what happens is this instead of giving 5 ampere, it will give you only 3.5 ampere. Because in the series circuit, the lower current always dominates. So because there is a reduction in the current, obviously the MPPT point will be changed. The MPPT point will be changed. So when the MPPT point is changed, even though this can give 5 ampere, this is not giving you 5 ampere. That is, even though you can extract 250 watts of power from the lower panel, you are not able to actually achieve that because of this reason. Another issue with this conventional system is, so this is connected to the system properly, but it is connected in this and you have an open circuit here. So what happens? The complete string will get open. No power will be generated from the circuit. See, this exactly has no problem with this. Only the second panel has got open circuited. So there is there is no option except the complete string of this system, string of the panels to be open. So that complete string will not give any power. So these are the major issues in the case of what you call this uh, conventional systems. So another issue is, suppose this panel is good, but this panel is degraded. So when I replace the second panel with the first new one, this is old one. Again, the problem persists. So this is 5 ampere, but this cannot give 5 ampere due to aging effect. Again, because it cannot give, this also will not give. So this mismatch of panels also will affect the total MPP of the system. So this is what I was talking about regarding partial shading. So this is what is the partial shading here. You can see the shade of a tree, and here the shade of the nearby building. So now when I talk about partial shading, I cannot say that I am the first person to talk about that. So there are many solutions which are already existing in the system or already existing in the literature. So the first one is using bypass diodes. So this is very well known and easy one, where each and every panel will have one diode in anti-parallel with this, or something of this kind. Something of this kind. So whenever you have this kind of diode, what happens is, when there is a partial shading on this particular panel, this diode will get activated and the complete panel will be isolated from operation. That is, even though this panel has the capability to deliver some amount of power, you are completely isolating it from the system. That is, you are not able to extract at least that amount of power which is available in the partial shaded condition. And another solution is, you will have different or multiple maximum power points during the partial shading condition. So we will always try to achieve this power point or that power using different algorithms, maybe optimization algorithm, maybe conventional P&O algorithm. So somehow we will try to achieve the global MPP. We call that as global MPP. Apart from this, the next one is array reconfiguration. So in array reconfiguration, what people do is they will actually reconfigure the complete system in such a way that the panels with similar irradiances will be joined together or will be connected together, and the others will be connected in different. I mean, all the panels will be connected as per the level of irradiance. That is actually a very good idea. However, the problem is once you need to check with the irradiance of each and every panel, then you need that many pyranometers. Cost. It involves a lot of cost. So that again has other issues like programming issues. And the next one is your distributed MPPT, where you have something like this. So this is your distributed MPPT, where you have each panel connected to each converter. So this is one solar panel which is connected to its own converter. This is another solar panel which is connected to its own converter. So when there is a partial shading on this, this will operate as per what the duty ratio given by its MPPT. And this will operate as per the duty ratio given by its MPPT. So if there is a partial shading or a shading on this, that will not affect the lower panel. Similarly, if there is some shading effect on the lower panel, it will not affect the upper panel. Something of this kind is a better solution. However, the problem with this kind of solution is each and every panel require each complete converter system. So this is a parallel solution. Similarly, we have this one is directly connected to inverter. So this is called a micro inverter, and there is one company which actually manufactures this micro inverter also, and these are series connected, and this series connected directly to the inverter. So these are the different solutions available. However, as I told you, each and every system needs one panel, one converter, which is not cost effective. And if you go with this kind of optimization techniques, you need it requires very high computational efforts and high memory requirements. And if you go with the conventional bypass diode approach, you'll not be able to use the complete panel. It's underutilization of panels. So in order to avoid all these things, there is one, I mean, this is a multi-port converter, which has been developed or proposed. So in this, if you see, so each panel is, instead of connecting to a complete converter, it has been connected to only one switch and diode. Similarly, this also is connected to one switch and diode, and they are connected in one way. So they are connected in one way. So that one way in which it is connected makes the both panels either in series but not in parallel. I mean, you can, if you want, you can connect in series. If not, they are neither connected in series nor connected in parallel. And this is given to the conventional boost converter followed load. Now, if you see, each switch which is connected in series with the PV panel operate at its own duty ratio. At its own duty ratio. So the same example what we have considered. So if there is a partial shading on that, this will give you 157 watt and this will give you 250 watt. So unlike the conventional system, you need not lose power of the bottom panel, or if you have used bypass diode, you could not have got this 157 watt of power. So the total power wastage, or we tried to take or extract maximum power from each and every panel under whatever the condition it is. So that is the advantage of this kind of multi-port converters. So, so the major advantages of this is, the first one is individual MPPT for each modules, which ensures maximum utilization of individual modules. simple and easy to implement. The structure is modular, reliable, and redundant. So, in case we have gone with four, I mean, here we have two panels. So, in case if you have gone with two different converters, you would have used two switches, two diodes, two inductors, two capacitors. But here you have used only one inductor and one capacitor, and of course, three switches and three diodes. And the count of inductor and capacitor will remain same even if you have two more inputs or four more inputs. So the complete system has only one inductor and one capacitor, which actually results in reducing the component count and increasing your system efficiency. Here, the control flexibility is high because when you have three systems, you have 3 degrees of freedom. You can control all the three switches independently. So the first switch will be controlled by the MPPT of the first PV panel. Second switch will be controlled by the second panel MPPT. The third one will be controlled for regulating the load output voltage. So this is what is your what is the advantage of the proposed approach. Now coming to the next one, it is the operation. So it can be operated in all the three modes: buck mode, boost mode, and buck boost mode. So here simply boost mode of operation has been shown. It can be operated in the other modes also. So now, so these are output voltage expressions for different modes. And now we need to show its validity. Like I'm telling that it is, but how? So first we have initially started with simulation. So this is what the conditions we have taken. The irradiance and the module for PV panel, whatever we have connected is shown here. And we have validated it in three different cases. The first case is partial shading. Second one is we have disconnected one panel, and the third one is the dynamic loading. So here, this is the partial shading condition. So there is a partial shading in second panel. So if you see here, if you see, I have suddenly reduced the irradiance for only second panel from 800 watt to 600 watt. So when it is reduced, of course, this is what is your settling time. It is a bit high since we are running in complete open loop. So the settling time is around 0.3 seconds. So what exactly happens is this will achieve its own MPPT at 600 watt. This first one will achieve its MPPT at 800 watt. And of course, since the total power is reduced because of irradiance effect on the second panel, the total power is the total load power is also reduced. So this gives us some proof that yes, because of partial shading, instead of completely losing the power from the second panel or second module, I can at least extract some amount of power from the second panel. Similarly, once when I disconnect the panel completely, so if you see here, I have completely disconnected the second panel, first panel all at once. So here if you see, when I have disconnected the panel, the voltage across the panel will be equal to the open circuit voltage. The current will be 0 and the power will be 0. Even in this condition, the first panel has not lost its MPPT. It is almost operating at its MPPT. And because, of course, because completely one panel is disconnected, the total power will be reduced. And dynamic load condition, so when you keep on varying the load, even then your maximum power point of each and every panel is withstand. So based on the boost converter equation, we have selected the different load values for each and every panel. So here you can see 1, 2 changes. So when there is a change in the load at different points, we get the the same maximum power. So the same should be taken on the real-time scenario. So this is the real-time scenario. We have used a PV emulator just to validate it. So this is the result for voltage, current, and power when there is a partial shading condition. So when there is a partial shading condition, here you can see this is the partial shading condition in the second panel. This has achieved its own maximum power point irrespective of the change in shading levels. Of course, the total power will be reduced. This is again sudden disconnection of the panel, and you can see the second module has achieved its own activity. And this is the dynamic loading. So we have changed the load randomly from this point to this point. We were varying the load continuously. So even then, within the variation of the load, the MPPT was able to adjust as quickly as possible to the load. I mean, it is able to set with respect to the load. So at different irradiance levels, we have tried to extract the maximum power experimentally. So in that case, it has been found that this proposed approach can extract the maximum power with respect to the in accordance to the standard or theoretical calculation. Not much deviation has been found. So this is a small comparison with the existing approaches. GMPP is global PowerPoint tracking, RNA configuration, and DMPPT. So when you compare this with the presented approach, you can see that in all the categories, mostly ours, the presented approach is having a bit better, what you call better performance. So reliability is high. It can handle multiple what you call module mismatch. Even it is fault tolerant and very heavy, having very high tracking efficiency. Sorry, I mean one FTP. Please message me. Okay, so sorry for the interruption. So this is what is the comparison, a qualitative comparison, and it is the quantitative comparison. If you see here, the number of capacitors, inductors, it is reduced when compared to the conventional approaches. For n inputs, you have only one inductor and one capacitor, which reduces the overall size and cost of the system. So this is what is about the multi-port converter. Now, however, the standalone multi-port converter, whatever we are using, it is only for DC loads. Now, what about AC loads? Now, when I come to AC loads, I'll just add one inverter, nothing except that. Even if I add the inverter, the advantage of this system is the input stage, which is having the multi-port converter, and the output stage, which is having the load along with the inverter. This was able to achieve the maximum power point under all the different cases what we have seen earlier. So this is what is the different types of different operating modes of this inverter. So here you can see the different modes when switch is on, one is operating, one is not operating, and all these things. So we have developed one control also for this. So this is a controller design which is based on this synchronous reference frame control. So here, if you go with this, this is a actually whatever the SRF controls were available, they are only, I mean, more predominant or more widely used for three-phase converters, three-phase inverters. But for single phase, it is a bit difficult to use because of one reason, that is there is no second signal. Like in case if you have ABC, three components or three phases, then ABC will be converted to first to alpha beta node and from there to DQ node. That is what is the Parkes transformation and Clark's transformation from we get this, I mean, from which is used to convert the voltages or three phase currents to the DQ axis. So for using this Sparks transformation in Clark's transformation, we need at least two signals. And those two signals were not available in single phase circuits or single phase systems. So what we have done is we have proposed one method, or we have used one method where that can be done. So using some delay process, delay of 90 degrees, alpha beta has been generated from single B node. And from there, it has been converted to DQ, and the remaining part remains the same. And we have used some optimization technique called genetic algorithm, a conventional one, to get the values of Kp and Ki. So these were the results. So here you can see, even with the change in irradiance, the output voltage was almost constant. Of course, as I told you, there is a small delay. So it is what is caused because of the MPPT technique taking time to achieve the maximum power point again. Similarly, this is the dynamic load conditions. So even with the step change in load, your output voltage was regulated and your maximum power point also has been retained. And this has also been connected to a multi-level inverter for grid connection. So far this is not grid connected. It is also a standalone system. So here we have connected it to a grid connected system. A similar type of controller has been used, and finally we have achieved that this can be, this is the output of a what you call this multi-level output, multi-level inverter output, and there is the output grid voltage and grid current. There is the grid voltage and grid current, where even after partial shading, because of the controller effect and the multi-port converter what we have used, it was able to achieve the maximum power point again. So for the change in load, you can see the voltage has been constant. Of course, since the load is changed, voltage is constant, your current will vary. Similarly, the reference voltage also, when it is changed, there was a small variation, and it was able to cope up quickly. Now, coming to this multi-level inverter, actually we tried only with the multi-level inverter, but somehow it turned out into a transformerless inverter. Now, what is this transformerless inverter? So initially, during the start of this presentation, I was telling you like there might be a small requirement of isolation for grid connected systems. So when I talk about isolation for the grid connected system, if isolation is not provided, you should not connect it. That is what you should not connect it to the grid. That is what the scenario is. But as per the German standards, if you have a leakage current which is less than 300 milliampere. Now, what is this leakage current? So this leakage current is nothing but the current which is flowing, or the current which you can find from the body of the solar panel to the ground, one way or the other. The body of the solar panel to the ground. Now, how does the current flow from body of the solar panel to the ground? So there you have something called the leakage capacitor. So that leakage capacitor, which is connected between the, which is there between this body of the solar panel to the ground. Because of that connection, there will be small current flowing into the inverter and from there to the grid. If that current is well within the limits, 300 milliampere, in that case, you call it as, if it is the case, then you can call that inverter, or you can directly connect that inverter even without a transformer. And those type of inverters are called transformer-less inverters. And as you have, as it is shown here, the leakage current, it is very less, which is around 100 milliamperes and less than the value of the so-called 300 milliamperes. And another advantage of the multi-level inverter here is the switching strategy, which is maintaining the capacitors always in a balanced state. You need not use, or you need not have any other mechanism to make the systems balanced. So these are the experimental results which we have used where we have taken the grid connection in the popularity and we have connected this and we got obtained these results. So this is what is about this. So here, this is what about all the things. But now I'm not sure who the audience are. Sir, are there any PhD pursuing or PhD um, just enrolled candidates in the audience? Hello? Hello?
The audience
Hello?
can
Am I
speak
audible?
now.
Hello?
Yes, sir. Yes, sir.
Yes, sir. Sir, the audience has all, I mean, any PhD just enrolled students or pursuing students?
Sir, can you check the chat box?
Yeah. So any students who are pursuing your PhD or just started your PhD journey? Anyone like that? Please ping or just raise your hand. I can just. I think only one has given yes. No. Okay. Anyway, so in case if there are any, I'll just give you some few inputs regarding this multi-port converters for various applications. So whatever we have dealt so far, that is with respect to the so-called multi-input converter. Now, this is a multi-input, multiple output converters. So here, if you see the multiple input, multiple output converters, this is one area where people have been working since the last 2 to 3 years. And this area is especially very useful for renewable energy applications and electric vehicle applications. Now, as I was telling you regarding the electric vehicle applications, there is one small auxiliary battery which is present in four-wheeler as of now, which is a lead acid battery of 12 volt, which is used for all these auxiliary loads like wiper, headlamp, uh, and all these things. However, that is costing, that also has some impact on the weight of the overall body of the vehicle. So people are trying to remove that as well. So when you remove that, you have a 192 volt battery with one motor running at that voltage around 192 volt. You need to regulate that voltage, so you need a converter. Apart from that, you need to step down that 192 volts to 12 volts or 14 volts for auxiliary supply from the same battery. So in that case, this multi-output inverters are one which is playing an important role. And the second aspect is people are now trying not only with battery-based electric vehicle, but also with hybrid electric vehicle, that is battery as well as supercapacitor or fuel cell. So battery will be acting as backup if it is a fuel cell based vehicle, and supercapacitor will be used for regenerative braking or backup or when there is sudden power requirement when you use battery based vehicle. So in that case, you have two inputs. So again, when there are two inputs, you need to have two converters. So you can replace that part with a single multiple converter or a multi-port converter. So this is one area where you can think of for working in the as a part of your PhD work. And another one is here. If you see, they both are DC loads. Now, when both loads are DC loads, it is not compulsory that all the loads will be having the same voltage. It may happen that some loads require 12 volts, some require 24 volts, require say some 36 volts. In that case, if you have different voltage levels, you can go multiple output converter instead of using 4 or 5 DC-DC step-down converters at the end. Because if you use 4 or 5 step-down converters, in that case, you need to have an extra cost for that. And another aspect is hybrid converter. So in this hybrid converter, what you can do is you can produce or generate both DC voltage as well as AC voltage. So you need not have a separate inverter again. You can think of some topologies where the output will give you both DC as well as AC. So if you can give that kind of what you call if you can develop that kind of converter, it will be very, very advantageous and it is very novel because you can have a DC-DC converter or a DC-AC inverter, but not DC-DC AC. So this is something called hybrid. And this, where do you use this? Especially you will use in this kind of what you call renewable energy applications, sustainable energy applications. Why? Because you need to supply the customers with AC loads as well as you need to supply the customers with DC loads. In that case, you need to have a DC converter separately. You need to have a AC converter separately. I mean, inverter separately. So all, instead of going with this, you can avoid all this with a single DC to, you can go with a simple DC to DC AC converter. That is a hybrid converter, which we can give you two outputs. So these are the two areas which you can work on. Apart from these areas, now the trending and what industries are looking into is use of WBG devices. These WBG devices are nothing but wide band gap based devices. So which are mainly the silicon carbide and gallium nitride based devices. So in case if you have good scope or if you have good facilities and time available, especially time available, you go through this silicon carbide and gallium nitride devices, their characteristics, and most importantly, their gate driver design. So when it comes to gate driver design, you need to have a very good active gate driver, which will turn on and turn off within less time. Apart from that, it should have very less parasitics introduced into the system. So this is where people are now working on. You can directly use them with the available gate driver, but in case if somebody are interested in this, you can work on this gate driver aspects of the silicon carbide and gallium nitride switches. One. Second one is you try to make a multi-port converter using those converters. Those switches like carbide or gallium nitride switches. Now, when you can make such kind of things, you will be, in case if you are MTech or BTech graduates, you can easily get absorbed into some good companies, core companies, where people are just starting their work on this WBG devices, wide band gap devices. So this is one important area where you can work on how to use that, what are the characteristics, what can be done to improve their what you call performance and all these things. Another important aspect or where you can work on is the reliability aspects. So when I talk about the reliability aspects, you should be able to calculate the reliability of each and every system. So if you can calculate the reliability of each and every system, that will be again another good work where you will understand why or how these multi-port converters are advantageous with respect to the single input and single output or the conventional systems. So that is one area where you can explore. Apart from that, I'll also I'll just I've already showed you this. So since there is some time available, I think I'll just continue for some time. Sorry, I'll, 1 second, give me one. Fine. So I was classifying this. Yeah. Now I was classifying this. Now how you remember the general structures and how you actually create one multi-port converters. I was talking about multi-port converters from the last, say some 45 minutes. Now, how do you exactly make this? So in order to understand how exactly do you make this, first we'll try to understand the general structures of some converters. So if you go with a non-isolated structure, here these are the general structures of non-isolated structures, where you have different cells, that is the source. What is a cell? Again, I'll come back to that. So different cells with a DC-DC converter. Simply you connect all these to a DC-DC converter, or use some magnetic coupling like interleaved structures, or you can go with, without magnetic coupling, you can directly go with EBU. EBU is energy buffer unit, or you can go with this kind of transformer connections. Now, when I call it as a transformer connection, here you can see this this is, you have one cell which is connected to DC to AC. It is not DC-DC, sorry. DC to AC, that is inverter, and all these are on the primary side, and this is on the secondary side. So you have one secondary and multiple primary transformer where you can directly connect it to the grid, or you have different cells connected to the DC to AC inverter directly, and from there a transformer. Similarly, unidirectional and bidirectional, which is capable of going with both the directions and only a single direction. This is again multiple input, single output, and multiple input, multiple outputs. So in multiple input, multiple output, you can have different cells at the input side and different loads connected in the output side. High gain and low gain. So if you have a transformer, you simply go with some sort of higher gain arrangement. If not, you can go with this what you call some arrangement in such a way that you can achieve very high gain. And low gain, you don't require anything, normal gains what you're using your buck and boost converters. So this is an example of modular structure and a non-modular structure. So here if you observe, if I wanted to remove this, simply you turn off the switch, take the source off. You need not do anything. Similarly, if you wanted to remove this source V2, it is not possible because you need to completely shut down the system. You cannot directly remove this. So this is called a non-modular structure, such kind of structures. And this is a modular structure where you can simply remove or turn off the switch, remove the source, keep a new source, again you give pulses to the switch. That's all. So actually, how are we trying to achieve or formulate this kind of structures? So it is the concept of what we call pulsating source cell, which means you know this very well, that you cannot connect two different voltage sources in parallel. That is, I cannot connect a 12-volt source with a 24-volt source. Similarly, I cannot connect 24-volt source in parallel with a 48-volt source or vice versa. So how exactly I can connect these two? That is the concept of pulsating source cell. So the pulsating source cell, they are divided into two types. One is called pulsating voltage cell, voltage source cell, and the other is pulsating current source cell. So in the pulsating voltage source cell, this is what we try to do. So we have a voltage source in series with the switch connected to a diode. So when the switch is on, you will have some voltage across the load, and when the switch is off, your voltage, output voltage across the diode will be 0. And this is a pulsating current source. So when you have when the switch is on, the output current is 0. When the switch is off, you will have some current. So again, this will be pulsating in nature. So we use these pulsating source cells. They in the previous slides, when you call a cell, it is a pulsating source cell. It may be an voltage source cell or it may be a current source. So when I have this, I need to follow some rules to design these things. So the first one is you can connect PVSCs in series and PCSC, that is current source cells, in parallel. Similarly, in rule 2, PVSCs can be connected in parallel. However, you need to have a proper switching strategy. And with each source, it is compulsory to have one switch in series with the source. And rule 3 is whenever you use these kind of structures, it is obvious that you will get some pulsating sources or pulsating outputs. And these kind of pulsating outputs should not be given to any of the loads. So it is compulsory to have some buffer units. This is what your EBU. That is your energy buffer unit or a filter. So LC filter, generally it is used in voltage source cells, and capacitor filter is used in current source cell. So this is how it is. Like first one is PVSCs which are connected in series. Second one is PVSCs connected in parallel. And the third one is PCSCs that are connected in parallel. So this is what is the general structure of a how these cells are connected in series and parallel. So this is with filters, EBU, that is filter capacitor RC filter, and EBU, sorry, LC filter and capacitor filter. So this is about how you actually design it. So I think I have next 15 minutes for your queries to be answered. So thank you. This is from my side. Thank you for your patience here. This is with respect to the technical presentation. Apart from this, I also, as already told, being the convener of IIC at NATPY, I would like to add something regarding this startups and the idea. Like, as you know, the government of India is promoting this Make in India and Made in India concepts. There is a wide scope for people who are working in these areas of design of converters for a specific application, especially electric vehicle and green hydrogen. Green hydrogen is another area where it is emerging. So if in case if people are enthusiastic about it, you can always have an idea of starting your own startup with respect to these things, and people are also ready to fund for this. So in case if you would like to visit any of the in case if you can if you get a chance, you visit any of the incubation centers or IIT research parks, you have a lot of scope to learn as well as to start your company from your side. So I think I'll stop here. This is from my side. Thank you. So if you have any queries, you can post it in the chat box. Or you can unmute if you have the chance, then you can ask.
സാറേ അപ്പൊ കഴിഞ്ഞു.
Sorry? Hello, sir.
Dear participants, any queries?
Participants, if you have, you can ask questions. Participants.
Yes, sir.
Participants, any questions? The group is full of silent. So what happened?
It seems no having any queries, sir.
Okay. Then, we can now wind up the session, right?
Okay, okay, sir. Yes, sir.
Okay, sir. Okay. So, thank you, sir. Thank you sincerely for graciously accepting our invitation and leading such a enlightening session. Your insights are not only information but also inspiring, leaving us with valuable knowledge to ponder and apply. We are truly grateful for the time and effort you are dedicated to gathering. So once again, I thank you for your remarkable contribution. Thank you, sir.
Thank you, sir. Thank you for the opportunity.
Thank you very much.
Thank you, sir.
So okay, sir. So next participants, next session will start at 7:30 sharply. So please stay.
Sir, can I leave?
Okay, sir. Okay.
Yeah.
Thank you very much.
Actually, I thought some 10-15 minutes discussion will be there, so I prepared
And
Hmm.
all are in this group, all are so silent. So what happened?
that is what. Okay, thank you.
Thank you, sir. Thank you.
Yes, sir. Yes, sir. Thank you.
Thank you. Arjun sir, shall we start?
Yes, we can start. Yes.
Sir.
Angela ma'am.
Okay, sir.
Okay.
Moving on, it's my pleasure to introduce our esteemed resource person, Dr. Narayan Unni. Dr. Unni has an incredible academic and professional journey. He completed his PhD research on thalassine thin films at MG University and went on to work as a postdoctoral research associate at IIT Bombay. Dr. Unni also contributed significantly to Samtel Color Limited, New Delhi, where he was deputed to IIT Kanpur as a visiting research engineer. His group achieved a remarkable milestone by developing India's first organic light-emitting diode-based displays. In 2008, he joined IIT Kanpur as principal research engineer and is currently a senior principal scientist at the National Institute for Interdisciplinary Science and Technology. He also serves as a professor with the Academy of Scientific and Innovative Research. Dr. Unni's work has earned him numerous accolades, including the prestigious CSIR Technology Award and fellowships from Kerala Academy of Sciences and the Institutions of Electronics and Telecommunication Engineers. He holds 3 patents, has led over 23 projects, and published 77 research papers. We are truly honored to have him with us today to share his expertise. Let's give him a warm welcome. Sir, please.
Thank you. Shall I share my slides?
Okay, sir.
Okay. Okay, slide is visible.
It is visible, sir.
Okay, so good evening to all. I will be talking today about building integrated energy efficient technologies for a sustainable future. So first of all, a disclaimer is there. Normally we talk about a specific topic. Say for example, I work on photovoltaic devices, energy storage devices, solid state lighting, and thin film transistors like that for workshops and academic conferences. But this time I thought, since this being something related to sustainability or something we need to talk about the measures that can be taken for a sustainable future, I have put together the activities in our division, giving special focus to building integrated energy efficient technologies. So it might appear a little bit disoriented, but at the same time, they actually focus towards what we can do in the building envelope to have a energy efficient system where sustainable future can be achieved. So we have activity on green hydrogen where we work on wastewater, which we convert to clean water and use water splitting, generate hydrogen. In fact, this hydrogen is proposed to be used to synthesize ammonia, and ammonia in turn shall be used for using Haber-Bosch process to generate hydrogen, green hydrogen. Another area is agrivoltaics, where photovoltaics and agriculture together are coupled, so that you can, it's like, Government of India has a motto, Annadada becomes Urjadada. That means you have somebody who is creating food, the same person will give us energy also. I will discuss agrivoltaics in a little bit details. Indoor photovoltaics is another area. We are all familiar with photovoltaics, because we all know the solar panels, rooftop solar panels and solar farms and things like that. But indoor photovoltaics is a rather new idea. So I will spend some time on indoor photovoltaics as well. In general, these ideas can be coupled with the smart buildings. I mean net zero buildings, where a building can generate enough energy to sustain its activities. Thermoelectric is another source of energy using thermo EMF, and energy storage is another activity. So these are the major activities in my division. Many of our colleagues have contributed to the slides today I am presenting. And I understand that Dr. Yaki will be talking about energy storage and Dr. Shukla will be talking about water and hydrogen activities. So I will try to focus on mostly on buildings. Okay, so with this brief introduction about the division, I will go to the presentation, but this is a very, very important quote from father of our nation, Mahatma Gandhi. The future depends on what you do in the present.
So whatever actions you are taking, you are responsible for that. And whatever good thing or bad thing may come out of your actions, you are the only responsible person. This becomes very, very important when you talk about climate change. So I have put a special topic about the climate change also in this present lecture. So with the quote in mind, United Nations has defined sustainable development goals. There are 17 sustainable development goals. First one is no poverty, zero hunger, good health and well-being, quality education, gender equality, clean water and sanitation, affordable and clean energy. So the seventh one is where our activities are focused. Affordable and clean energy. 8 is decent work and economic growth, industry innovation and infrastructure, reduced inequalities, socio-economic inequalities, I suppose, sustainable cities and communities, responsible consumption and protection, climate action. This is also something which we will touch upon in this presentation. Life below water, life on land, peace, justice, and strong institutions, partnerships, and for the goals. So these are the 17 sustainable development goals. Just for the complete information, I covered all the sustainable goals. Now, what is the importance of building integrated technologies? Because we all speak about building integrated technologies. 80% of time, the urban population spend indoors. That could be your house, that could be your classroom, that could be your office room, or a movie theater, wherever. But 80% of time you are spending indoors in general. This is an urban condition. And 40% of total energy consumption in cities, particularly, is taken by the buildings for its lighting, for its air conditioning, for its cleaning, for the transportation, that is lift, all those things. 40% of energy consumption will be taken by the buildings. And also the sad thing is that 25% of total greenhouse gas emission, buildings are responsible for this. Again, this is due to air conditioning and many other things. But apart from that, the construction materials also, the process in which this cement is manufactured and all those kind of manufacturing activities, if you add, then it will be much more than what we generally see around. So 25% of total greenhouse gas emission is also from the buildings. The new concept is net zero energy building. So what is a net zero energy building? A building can be a source of energy also. There can be rooftop solar panels. There can be windows which generate energy. You will see that. But earlier these were solutions, but now these are solutions with aesthetic appeal. And this picture shows a Phipps Conservatory by Design Alliance Architects, Pittsburgh, Philadelphia, probably one of the first buildings with smart windows and rooftop solar farms and things like that. See, people like me, that is around between 50 and 60, that is the age, when the glass facades started coming to cities like Mumbai, Bangalore, we were initially surprised why this kind of a construction is coming to India. Is it good for our country? We don't know. But anyway, now they are already there. So what can we do? We cannot anyway demolish those buildings. But what we can do is we can probably convert those glass facades into something which we can use to control our energy usage for the building, something which we can use for generating power if possible. So this is a mitigation attempt. Already the bad things are there with those kind of things, but still some good thing may also come out of that. And there are two strategies. Passive strategy is having smart architectural design, building geometry and direction, natural lighting. So wherever possible, you will take sunlight instead of bulbs and all, and good ventilation instead of air conditioning and fans. These are there. If you see the buildings designed by our architect Shankar or Larry Baker, you see that it is possible to use nature's resources to the maximum so that our electricity consumption can be reduced. Active strategies include installing energy saving systems, photovoltaics, smart thermal management, and lighting. So this is what today we will try to discuss a little bit, because passive strategies are there, even though it is very, very important. Today, I think we need not go to that. Energy devices R&D for buildings at CSIR and IIST. These are the different areas for energy devices. We have light emitting diodes. So like this is the energy efficient lighting and indoor light harvesting mostly using dye sensitized solar panel. This is a different solar cell technology. Then smart architectural planning, having windows at the optimum position, energy simulation studies on buildings, energy generating flooring. This is what is called a smart flooring with the piezoelectricity, triboelectricity, those kind of things are used for this. Powered by indoor energy harvesting technologies, IoT-based systems are there. Waste heat harvesting using thermoelectric technology is there. And then light channeling using dynamic power windows with the refractive index matching is possible. Thermoresponsive windows are there. These are stimuli responsive materials. The stimulus can be temperature, the stimulus can be electricity. Both ways, these are dynamic windows. Sometimes the very same windows can actually generate some electricity also. So this is a typical cartoon of a smart house where what you can do to make a house net zero. Now, I wanted to spend some time on this green revolution too, fueled by even solar sharing agrivoltaics. I will come to the importance of this for buildings in a minute, but otherwise, this is really a very, very interesting technology. Before going to building, I thought I will tell you what is the agrivoltaic technology. So you all know how solar panels are kept. This is in Rajasthan, Thalia 2.2 gigawatt plant. It requires 56 square kilometers. Okay. So electricity transmission and distribution loss is 20%. You all know that. So whatever you generate here, 2.2 gigawatt, think about the 20% loss that will happen during the transmission and distribution. So what we require is definitely not this kind of very, very big solar farms. Second thing is it will lead to solar desertification because nothing will grow under these solar panels. And you are actually creating another desert in this land, arable land. So that is what is called solar desertification. But decentralized electricity generation and distribution will definitely be the answer. Now look at the map of India here. So arable land, forest, non-agricultural plantations, scrub and grass, unproductive land. This is all mapped here. And most of this will be taken for solar panel installation. If you actually want to reach our target of this 500 gigawatt of renewable energy capacity by 2030. But whatever land at the moment proposed, 46% of the land suitable for cultivation. Globally, there is a 20 to 40 times increase in land requirement for photovoltaics by 2050. This is a data from US Department of Energy Solar Future Study 2021. So the question is, are we going to use our farmlands to meet land requirement? Or is there another way of looking at it? Now look at the solar insolation. This is a solar flux. Solar flux, we have a lot. We are actually blessed to have so much solar flux. So if you look at the color code, it shows 800 to 850 watts per square meter. Half of the India is having that kind of solar flux. But we don't need that much for our solar panels. And agriculture. Agriculture requires less than 30% of the solar insolation that we are currently receiving. So that immediately leads us to a plan where we can use 30% of the solar insolation only. So you need to have only some area where the 100% of solar flux you can distribute to a larger area below. So that means you can diffuse the solar flux from open areas to larger areas beneath. Now think about these large areas being kept between solar panel. So this is exactly what is called agrivoltaics. And excess solar insolation is not good because it increases thermal stress for crops. It reduces land water table due to increased evapotranspiration. That means you evaporate the water from the earth surface. So the water tables will go down. Now, agrivoltaic is a farming and energy from the same land. That is why earlier I told Annadada becomes Urjadada. So it is a motto of Government of India. Doubling farmers' income is the priority there by decentralized energy generation and use. You see, normally earlier it was done like this. You will have solar panel and in between there will be open spaces and you can have some kind of a cultivation. So food processing, cold rooms, electricity to communities. This electricity can be used for several purposes. It can be used for irrigation and drinking water, water for animals, increased crop yield, crop protection, say freezing and other things, improved microclimate, food, energy, water nexus. These three things can be definitely supported by using agrivoltaics. So problem to be addressed in agrivoltaic sector. Now we understood that what is agrivoltaic, you will keep solar panel and you will have cultivation in between solar panel. Fine. Is it okay? It is not okay because there are two types of agrivoltaic. One is vertical clearance more than 2.1 meter, that is category 1. And the second one is vertical clearance less than 2.1 meter. It all depends on the shadow cast. That's it. Now here, if you look at it, you will see large vertical clearance increases structural cost. Your engineers, you should be knowing that structural cost is very, very important. And so this is a shade spot and this is a bright spot where it is open. And when you keep cultivation, you see that this again, you have a shade spot, bright spot, and where you want to keep the plants, you are not very sure. Another interesting thing is that we can utilize the untapped solar spectrum, around 20%, to enhance the desired photosynthetically active radiation. The entire solar flux is not required for plants. It depends, varies from plant to plant, but still there is a particular power for a particular variety of plant. So you can have some sort of optical solution where the solar flux will be transmitted to that, which is matching perfectly with what is required for the plant. So even distribution of power towards the shadow cast region of PV modules, you can increase the electrical energy generation by increasing the PV coverage area. See, for example, if you look here, this much area is open. So you could have actually created more electrical energy if this area is reduced. You can have more panel, but then your sunlight is reduced there. But that sunlight you can evenly distribute below the solar panel by using a proprietary optics developed by CSIR and IST. This work was led by Dr. Adarsh Ashok from our division. Okay, now if you have seen that video, this actually got a National Research Innovation 2022 award for SEBI Clean Tech Challenge 2023. You see that the red portion, this is a polymer nanocomposite based screen and a lot of simulation, lot of material science has gone into it, but this can distribute the sunlight evenly below the panels. So module level agrivoltaic standard installed for the first time. Spectral conversion functionality is added, 5% enhancement in the photosynthetically active radiation when compared to state-of-the-art agrivoltaic systems. Spectral conversion functional under diffuse sunlight and low light conditions, assuring the supply of photosynthetically active radiation even in low and diffused sunlight. And this technology offers a 14 to 21% increase in the PV coverage area when compared with the standard category 1 and 2 AV solutions. Precision radiation control enables a favorable microclimate because you are not directing the sunlight just like that to earth surface. So your evapotranspiration will be less. So water tables can be retained. Now, this is a better picture. Here you can see that in this area, open and closed regions are there. So wherever the panel is there, there's a shade spot. And wherever it is open, you have bright spot. But when the even solar light sharing optics platform is installed, here you see even light distribution. Light is evenly distributed across all the gaps. So this is a proprietary optics. Okay, this is not as simple as it looks like. But now, having said this, we come back to our buildings. So we have an ongoing project, field deployment of planar optics based 3.6 kilowatt peak rooftop agrivoltaic. May 2024, this started. And here in the building. You see, this is a conventional rooftop farming. You just have the rooftop farming with a kind of a shed or something. But this is the rooftop agrivoltaic, number one, where you have solar panel, you have open space, you have our proprietary optics. So light is distributed uniformly across this area, and you have the plant growth. This project is funded by State Renewable Energy Agency, which is ANAT. The project highlight is that this marks the first ever global demonstration of building integrated even solar sharing agrivoltaics. So what is our vision here? Our vision is the Green Revolution 2. Pioneering sustainable energy and farming with the CSAR solar light sharing technologies. With that, where are we going now? We go to photovoltaics. Second topic, light energy to electrical energy. Solar cells obviously is the first choice. What are the parameters you consider? Efficiency, power efficiency, of course, durability, cost, payback period. So think about silicon. Silicon efficiency is very high. Monocrystalline silicon, something like 25%, 23% efficiency is there. And multi-junction silicon, if you look at NREL chart, it will say 46% or something is a world record now. 4-junction solar cell with the concentrator, but then cost will be high. But durability is also good. Silicon solar panels can go probably up to 20 years without any problem. And the payback period is also, you put a 2 lakhs or something for a 1 kilowatt panel. I mean, not 1 kilowatt, it will be more than that with 1 lakh, right? But you put it, what is the payback period, you can calculate. This is one way of looking at it. But solar panel, you know, there are 3 generations. I don't know whether you are familiar with the 3 generations of solar panel. The first one is first generation, which is single crystal silicon. Second one is thin film solar cell, that is monocrystalline silicon and another thing. Third one is third generation solar cell, of course, which is organic photovoltaic, dye sensitized solar cell, quantum dot solar cell, perovskite solar cell. This kind of third generation solar cell. So today we will discuss a little bit about dye sensitized solar cell. So this is, for example, a facade at EPFL in Switzerland. These are all solar panel. Since the dye is organic, you can actually tune the chemistry and you can have different colors. Okay, and this may be possible to install the solar cell in other application, but this is of course the first generation solar cell, and solar cells are used everywhere, including our satellites and all. Okay, fine. But what we are trying to discuss today is that most of our building integrated requirements, like our Bluetooth devices, our remote control, and small power applications, sensors, temperature monitors, all those things use batteries, right? And what happens to these batteries once the lifetime is over? Most of us throw it into landfill, and they rust, they release toxic chemicals, and situation becomes very, very bad. Unless weird, I would say. So a lot of batteries are just thrown. If the number is, you know, with the IoT is coming into its peak, 3 trillion sensors are going to be installed per annum. And how are we going to power all these sensors? If you really want to do with battery, button cell and all, then you are admitting that you will be throwing away millions of used batteries into Earth, Mother Earth, which is also not going to. So this is where we try to have a simple solution. Maybe some of you know what are dye sensitized solar cell. This is again an electrochromic solar, electrochemical solar cell. Okay, this is slightly different from our PN junction solar cell or simple semiconductor based solar cell. Professor Michael Gretzel from EPL, in fact, devised this solar cell initially. So they have a dye. So dye, when absorbs light, as in other organic materials happens, you have an electron going to the LUMO level. And this, since there's a driving force between the TiO2 and the dye, it is just falling into the conduction band of your electron transport TiO2. And this is just going into the photoanode. And the dye cannot stay like that because dye lost 1 electron. Dye is getting that electron from a redox mechanism. This is an electrolyte. So you get an electron from there. And this electrolyte will get that electron back from the counter electron. So in the external circuit, when you connect these two electrodes, you will have an electron. This is in very, very simple terms. This is how it works. But at the same time, time scales are also important. So you can see that the electron injection from the LUMO of the die to the conduction band of your TiO2 happens in 100 femtosecond. But at the same time, the electron from here can go back to the die, it can go back to the sensitizer, it can go back to electrolyte. But these processes are generally long time. It takes 500 microseconds or 500 milliseconds. So this is a faster process. That is how it works like a solar cell. Now, this is there, I think from 2000 or something like that, it was there. But nowadays, there is a very, very big interest because there is something called indoor photovoltaics. And we see that in indoor photovoltaic, DSSC has become the most efficient solar cell. So normally, we can harvest energy from the atmosphere. You can have radio frequency capture. You can have light, you can have piezoelectricity, you can have, thermoelectric generators. All those things are there. But indoor photovoltaic is like a lot of ambient light is there. So have something which will harvest the ambient light and generate electricity. Theoretically, it can go up to 57%. And what is the advantage? It's widely available. Maximum power density is there. Ease of integration into different artistic structures. You can have pleasant aesthetics with this. Integrating indoor light harvesters to IoT devices, Internet of Things devices, will render the future wireless networks sensor autonomous. So you don't need a battery. If at all you need a battery when you switch off the light, it can be a storage cell. And since you are not discharging it all the time, the life will be extended. So I am proposing that we substitute battery with DSSC panel. If that is not happening, your storage cell lifetime can be extended. Even that itself is a very, very good thing. So it provides greater reliability and operational lifetime. Energy harvesting not only reduces the number of batteries ending up in landfills, but also lowers the volume of mined raw materials, thereby improving the entire value chain. Think about lithium, think about the zinc, all those things in battery you are using without any control. This is something which we need to control. Now think about the ambient light. So near a window opening to external world, you have a 5000 lux, very, very high brightness. And near your working desk, it could be 600 lux. And in the office wall, 50 to 300. In the storeroom, 500 to 700. In a shelf, again, it is a diffused light, 50 to 300. But, in a classroom, it may be more. In an operation theater, for example, it will be 3000 to 4000 lux. It's a lot of light. And what do we do with this light? And now look at this graph. It is a Shockley-Queisser limited power conversion efficiency with AM 1.5G, which is 100 milliwatt per centimeter square. It is coming around 34%. This is a single absorbing material. This is the maximum that you get considering the absorption spectrum. But this efficiency can go if you have a material. See, silicon, what is the band gap? Something like 1.1, right? And if you have a material which can have 1.6, 1.7 band gap, it can absorb in the emission matching to that of the ambient lighting, it can go up to 57%. This is a theoretical calculation. And think about our lighting sources. This is a 3000 Kelvin color correlated temperature. This is a 4000 Kelvin one, this 6500 Kelvin. I'll come to this later when we discuss lighting. But what are these numbers? 3000 Kelvin, 4000 Kelvin, 6500 Kelvin. Ever looked at the holder of a bulb? It is written there. Okay, I'll come to that. So this is the emission spectrum of a fluorescent lamp. And this is the emission spectrum of a LED lamp. You see, this is very, very sharp. But this is a bit broad. So you can actually harvest more photons using an organic dye. If you properly design, if you properly tune the chemistry of the dye, it is possible to harvest a lot of photons from ambient light. This is exactly what we did. So in the DSSC, we can work on transparent conductive oxides. We work with the fluorine doped tin oxide. And we fabricated dye sensitizers solar cell perovskite also we work. Okay, multi-junction, photocapacitor. These are different activities, but our activity is focused on chemistry, where new dyes are designed, synthesized, new electrolytes, small molecule based additives, which improves the mobility or increases stability, new hall transport materials. Okay. And on the material science side, new semiconductor materials, you can have TiO2. You can have some other oxides. You can control the morphology. You can control the thickness. You can control the mobility. Those things you can work. Perovskite, various materials are there. And counter electrodes, normally platinum is used, but one can try reducing the content of platinum. You can look for other things. In device physics, device fabrication and interfacial device measurements, normally done with impedance spectroscopy and things like that. And when you go for engineering, equipment design and development, we had a big project where we have our own pilot line for fabricating dye-sensitized solar cell. So we can fabricate modules and you can have product integration. So if you look at the kind of energy landscape, very, very small energy is generated from indoor photovoltaics, but from a very small area. Efficiency is high, but the input is low. So even with a high efficiency, output will be low. But this microwatt power is enough to support many, many IoT-based sensors. And if you can generate a little more energy, it can be used for portable electronics. And once facades and all, you create close to megawatt, then it is used for building integrated photovoltaic and transport integrated photovoltaic. There's a plan to have photovoltaics in trains and all. That is what is transport integrated photovoltaic. So our achievements in technology description, we achieved indigenization in developing equipments for indoor photovoltaics. So this photograph I have given is some 500 robot, which developed with a Bangalore-based company. Because in the interest of time, I'm not going into all details, but there are several processes, several screen printing processes, dispensing processes. This can be done in our laboratory. And we have developed an end-to-end decentralized ecosystem, supply chain in terms of materials and coatings leading to import substitution. Successfully introduced indoor light harvesting with efficiencies more than 40%. The latest publication has appeared in JMCA, Journal of Materials Chemistry. With again, this activity is led by Dr. Suresh Soman, aligning with Government of India initiatives, Make in India, Atmanirbhar Bharat, Make for World. These are our motto also. So advanced R&D is there with the turnkey solutions and innovative applications. This picture is the very first prototype of a mobile charger which we generated. These are all panels, okay. So this can be kept in a brightly lit place, and this can be a mobile charger. So this is state-of-the-art indoor PV performance from NIST. Now 35.6 was the record until last week. Now we have something like 40%. Okay. Now how this is happening? We synthesize dyes. Their absorption spectrum is perfectly matching with the their absorption spectrum is perfectly matching with the emission spectrum of the lamp. So wherever the lamp is emitting, there the dye is absorbing. So the absorption process is so big, you absorb a lot of photons and you generate a lot of electrons. So that is why your efficiency goes higher and higher. Then you work on the device physics, you control the loss mechanisms, you control the recombination pathways, then you are getting very good efficiency. That is how it works actually. So these are some of the aesthetic things. These are our lab level devices. These are our modules, and these are the panels. Okay, and this is a artistic installation, and this is a solar cell. This is the solar cell. This is a solar cell, and because of the power generated from the solar cell, this is a sensor head. There's a sensor which will tell us what is the ambient temperature, 27.3 degrees Celsius, what is the ambient humidity, 62%, and time, and sometimes you can calculate the air quality index also. And this lantern is also, lantern doesn't work, but it is a interesting installation. So why this becomes very important for buildings? Why this becomes very important for air quality monitoring? Because indoor air can be 5 times more contaminated than outdoor air. See, once I was going to airport with some colleagues who came from SECRI, Central Electrochemical Research Institute. He had one air quality monitor with us. So air quality, we were looking at how is it. And the number when we started, and the number after we reached the airport, we looked at, because it's an AC car, simply it went close to 10 times. So this is the way, because CO2, it is increasing when all the windows are closed, even though there is a circulation using air conditioning, but that is how air quality is degrading in closed spaces. And sources of air pollution are, of course, chulas, tobacco if somebody is smoking, dust is another one, mosquito repellent and sprays like that, wall and furniture paint. For example, this car, if you park in sunlight, you go back and there's a bad smell. This is because the artificial leather resin will release aldehydes. Very bad. Aldehyde is also carcinogenic. You breathe in, there is a chance that some other issues can come. And wood and paper burning, no need to say CO2. Outside air from vehicles and all, carbon monoxide, carbon dioxide, and whatnot. So this is there. And solution is that we monitor, but we monitor with battery. So that is where our technology, as I mentioned, is coming in. So this is our aim. Portable indoor temperature, humidity, VOC monitor powered by CSR NIST developed indigenous indoor light harvester. Reharvesting and reusing indoor light. Lot of light is there. Use it because you don't need so much light. This is only, see, these are the panel. So brightness of the room will never get decreased because this panel is a small one. It has a size of probably 2 mobile phones together. So this is a photograph of a sensor we developed in CSR and ASD. And these 3 sensors are here. This is the first prototype with 2 sensors. 2 panels. These are 3 panels. So this is telling us about temperature and humidity. So key features are indoor light harvester inspired by photosynthesis. See, I forgot to mention that DSSE works very, very similar to photosynthesis. Exactly this is what is happening in photosynthesis. 40% efficiency under indoor light is possible, more than. So consider 40 AAA batteries saved in 10 years. That means you are reducing 2,500 grams of carbon dioxide in 10 years. Low cost and maintenance free. If someone is going to Trivandrum Airport, domestic airport, I suggest that you go near the VIP lounge. One of these is kept there. And when you come back, the arrival lounge, you can see, unfortunately, I forgot to put a photo here. A Theyyam type of a structure is installed near the arrival lounge. And there is also an air quality monitor, which is powered by our DSC panels, has been installed. So kindly have a look at it and take a selfie with that and spread the message. Okay. Now, again, I think need to take more time on this because this is done. But these things can happen only when there is an academia, industry, and user partnership. A scientist sitting in lab alone, it will not work. You need to have meaningful collaborations. It is not about publishing a paper. It is more about coming out with a product. So we have our partners. We have Elixir Technologies, to whom we transferred our technology, and now Embedded Private Limited, a Bangalore-based startup, and they have come up with solutions for particulate matter PM 2.5, CO2 sensor, and the total VOC, volatile organic compounds, and ozone sensing. All those things can be done, and it is very, very important for places like airport, metro stations, and all. So this is the right way of doing it. In our we have a conviction that this is what we need to do. Another activity is perovskite solar cell. As we all know, perovskites are very, very efficient, going up to 25-26% efficiency now. Only thing is that very sensitive. So one can actually fabricate only in equipments like this. This is a glow box. Inside there is a controlled atmosphere. The humidity will be less than 1 ppm. Oxygen will be less than 1 ppm. Only then these materials will be stable. But you encapsulate, you can take out and work outside. And this is an evaporation chamber. You can slide the door, keep the material inside and do the electrode evaporation. All those things can be done. So our strategy is we use optimized perovskite compositions. Perovskite is, those who know that, they know that it is ABX3 with certain cation and anion compounds. So use of optimized perovskite compositions and appropriate interlayer, reducing the number of interlayers and replacing costly metal contacts with carbon. So all reported perovskite, most of the reported perovskite solar cells with a very high efficiency are using gold as an electrode. So think about it. Can we have large panels with gold? Impossible. We can have it, but it will be very, very costly. So our research focuses on having carbon as the electrode. So this is also a useful way of using the carbon. Okay. So this can be printed, this can be sprayed. So this is a basic structure of this. You have a transparent electrode, fluorine dropped in oxide, and this is again an additive layer, perovskite whole transport layer, and this is perovskite with passivator. PCBM is an electron transport layer. PCP is an exciton blocking layer, silver electrode. Sometimes we use gold electrode. So instead of this, when we use carbon, still we have something like 14% efficiencies. And this will die very fast. But carbon-based perovskite solar cells are stable under 80% relative humidity for 50 days, 1200 hours unencapsulated. You see the power conversion efficiency is almost stable up to 1200 days. So this is a big achievement that we have developed perovskite solar cells with longevity, even though efficiency is not comparable. We admit efficiency is not comparable with the normal efficiency reported by perovskite solar cells with gold electrode. And our major activity was on whole transport layer free perovskite solar cell. Indoor light harvesting, we put perovskites also. See, perovskites have a problem. Lead is there. So I don't know how far we will be able to use it. But we also use lead-free perovskites. And these also have very high efficiency under indoor. So what is our vision here? Our vision is enabling India's journey to Atmanirbharta using advancements in indigenous indoor photovoltaics at CSIR. Now, what is required for a building? We need solid state lighting. I already mentioned we can have light tunnels, which will bring in natural light, but not every building can have it. So what do we need to do? We need to have artificial lighting. This is what I was asking earlier. Look at the holder of any bulb, LED bulb, for example. Have you looked at these numbers? Your electronics people must be knowing power factor. I will not say what it is. But 6500 Kelvin is written there. Lumen is the power, unit of power perceived by eye. This is somewhat equivalent to watt. Watt is the unit of electrical power. Lumen is the unit of power perceived by your eye. Okay. But what is the 6500 Kelvin? This is the correlated color temperature, which means this is the temperature of the black body, which will emit light exactly similar to this bulb. So 6500 means it is a white which is close to the blue. 3500 Kelvin means which is a light close to the yellow. So if you remember our incandescent bulb earlier, some 20-30 years ago, we had incandescent bulbs. Those have a yellowish light, right? So they are 3500 Kelvin, 4000 Kelvin. But nowadays, the LED bulbs and tubes, they are more towards the blue. This is 6500 Kelvin. Okay. So Edison invented electric bulb, we all know. This is the first bulb which is kept in museums and National Science Museum. December 1879. We are again in another December, right? And Peter Cooper, he invented the fluorescent lamps, but this was long. So Edward Hammer in 1976 devised this compact fluorescent lamp. The length is there, but he made it bent like this. Marvels of lighting technology. But then came LEDs. So these are inorganic LEDs, point source. And this is organic light emitting diode. This is a planar source. This light will be unpleasant. So we'll put a diffuser to make it look like this, planar. You put it, then what happens? 30-40% light is lost there itself. So even though these are very, very energy efficient, it may be good to have some sort of a planar lighting solution. That is where organic light emitting diodes are coming into picture. Okay, we'll quickly see that. I will not spend much time on this because this is the technology already in market for LEDs, and OLED is still in the research for lighting. But OLED is also in market for mobile phones as a display component. Mobile phones, television screen, laptop screens, all are there with OLED. So history of electroluminescent diode started with 1907 and 1979. Shuji Nakamura, he got a Nobel Prize a few years ago. Nikkei Corporation made the first blue LED. There's, this story. There's a PN junction, and electron and hole recombined here, emitting light. Certain conditions will have to be met. So this is the standard structure of a inorganic LED with the anode. From here, holes will be injected. There's a p-doped hole injection layer, hole transport layer, and EML. And from the other side, electrons will be injected. There will be n-doped electron injection layer, electron transport layer. So here, electrons will come from this side, holes will come from this side, they recombine. This is an organic LED, and this one is an inorganic LED with the gallium nitride. More or less, things are similar, but in here it happens with the PN junction. Here it happens with an emissive layer. Nakamura, I already mentioned the kind of material he used. Now, OLED, I was saying OLED is the next generation lighting. So incandescent bulbs, 15 lumen per watt efficiency. Fluorescent tubes, 90 lumen per watt. Inorganic LED, 169 for white, but for other color, it is going more than that. Organic LED still around 100. And Department of Energy roadmap is targeting 165 lumen per watt by 2025. Lot of advantages for organic LEDs because it is a green technology. It is a planar technology. Many things are there. I'm not going into details, but functional mechanism, if you ask me, there is charge carrier injection from both electrons. Charge carrier transport towards emissive layer. And electron hole pair is called exciton. Exciton formation and then exciton recombination, which results in photon emission. So this is the first organic light emitting diode with a molecule called ALQ3, trihydroxyquinone aluminum, is organic. And these are the two gentlemen, Tang and Manslake from Kodak Corporation, Eastman Kodak. They developed the first organic light emitting diode. Now, this is a video from a company called Novalet from Germany. They are working on solid state systems. The possibilities of planar light emission sources, the possibilities of flexible light solutions. That means the possibility of OLED lighting solutions. Color can be controlled. Anything can be a lighting source. Look at those windows. This is in night, and the window itself can be a light source. Okay, so these are the possibilities using this technology. With that, I am going to the next topic, smart windows. It's an important topic considering the urban agglomerations in India. A lot of migration is happening, right? People are from villages. Without an end, people are moving to cities for job, better education. Many reasons are there. So India is witnessing the biggest urban migration of the planet. Think about urban migration trend in millions and millions of people. This is the percentage or something. It's given here. Each minute, 25-30 people are migrating to Indian cities from rural area. Indian urban population is projected to reach 60 crores by 2030. And why they are migrating? They migrate for better livelihood and lifestyles. So these are the reasons, they get smart homes, traffic control, transport. So parameters you need to control when the urban population increases like anything. You need to provide energy, healthcare, education, water, waste management, communication, I don't know what not. But we need to promote cities that provide core infrastructure, give a decent quality of life to the citizens. Inclusive developments of compact areas through retrofitting and redevelopment of existing infrastructure. Create a replicable model for the future cities. Developing smart new areas, green fields around the cities, a green envelope. Unfortunately, many of our cities, which are the hot destinations, they do not have it. Look at the air quality of Delhi. You might have seen in television, right? So electrochromism is some technology using which we try to address this uh, in our own way. The reversible change in the optical properties of a material by application of electric voltage or current. Electrochromic materials change their absorbance or reflectance via an electrochemical redox process. So DSS is an electrochemical device. Electrochromic device is also an electrochemical device. There are three categories. The first category is soluble in both reduced and oxidized states in a given electrolyte solution. So it will remain as liquid. And the second one, soluble in one redox state, but form a solid film on the surface of an electrode following electron transfer. Some kind of intercalation happens, it will go and touch the other. Then again, the transmission changes. Third one, both or all redox states are solid. These are thin films. These systems are studied as thin films on electrode surfaces. Inorganic materials like tungsten oxide, polymer equivalents, conjugated conducting polymer, Prussian blue, all those things. So this is again another video, metal oxide electrochromic devices. Quickly, I will show how it happens. So you have these different layers and ions are ejected from, you apply a voltage, ions will come to the electrochromic material. So oxidation happens or reduction happens, which changes the band gap of the material. When you change the band gap, what happens? Its absorption changes. And why this technology becomes important? Because energy saving fenestration, that means windows, using smart windows. So look at the IR image of this building. So energy flow, 30% of energy waste is happening through windows. And 50%, more than 50% energy transmission also happening through windows. That means when you don't want sunlight come inside, heat the room. And when you heat the room, the heat energy is going out of the room. It's like it works. And that is where electrochromic glass market is there. You can control the transmission. It's a very big market, projected to be 2.6 billion by 2027. Okay. So coloration is possible and it can be used as a battery also. Electrochromic coloration, there will be charge and you charge it, you have to apply electrons. You bleach it or you discharge it, these electrons will come back. So it is like a capacitor. You can keep it as a kind of a storage device also. So different energy saving and privacy modes are possible. And peak energy saving could reach up to 30 to 35% by changing the transmission rate. You don't allow light to come inside. You don't allow IR to come inside. It can be used as a secondary energy source. Not very efficient, but it can be used as a secondary energy source during non-working hours. Dr. Bishwapriya Devi is the activity leader here in my division. You can see this video. You apply a voltage, it changes the color. And you apply a reverse potential, it is going back to its transparent state. All this is possible. See, this is how it works. So the important parameters are coloration efficiency for a window, how much you can change. Optical density, that means the transmission, how much you can control. Contrast ratio is a difference in transmittance in the visible spectrum. Response time, how fast you change. Those who have traveled in flights, Dreamliner and things like that, you know that windows have shutters which changes color by applying electric potential. But it is actually not electrochromic. There is something called SPD. So they are suspended particles. They will go and attach to an electrode. That creates a kind of a shutter. And right erase efficiency is very important. Cycle life is very important. Forget these equations. This is about delta optical density. Okay, not going into those things. But applications are smart windows, smart mirrors, displays, electronic papers, e-skins, smart tags, charge state indicator, sunglass. Of course, you're very familiar with the sunglass, which is not electrochromic. Okay, it is photochromic, but you can have electrochromic sunglass also. So again, printed labels also, because you control the reflectance, then you can use it like a LCD also. So smart windows, these are some smart windows from our division. Electropolychromic switching. Depending upon different oxidation state, you can have different colors also. And this is thermochromic window. There is no electricity involved. It is only thermal change. So LCST is the technology, lower lower critical solution temperature. Here, there is something, you increase the temperature, the turbidity of the solution. These are two glass plates and a liquid is filled in between. The turbidity of the liquid changes, then the transmission changes. So 25 degrees Celsius it is transparent, 32 degrees Celsius it is opaque. And this temperature window we can control if we work on the chemistry of that. And this is large area photochromic glass. This is light only is a stimulus here. So these are smart windows. Smart means what? There is a stimulant. In response to that stimulant, the transmission changes. It can be heat, it can be light, it can be electric pulse. Okay. And applications I already mentioned. Another very important thing is NIR harvesting, organic photovoltaic. I did not go to organic photovoltaic, but organic photovoltaic is also a very important area. And nowadays it is being used for window applications. And this publication is a university. I forgot the name of the university. I didn't put it here, but of course in US. And the university tower as seen from an organic photovoltaic panel. So this when the window is open and this is through the panel. So panel is transparent. How it can be transparent? How you can have a photovoltaic cell which is transparent? Transparent means the visible spectrum, visible radiation is transparent. But solar radiation is not having only visible. It will have some amount of UV, some amount of NIR. And these solar panels use only that IR. So IR is absorbed, but visible is transmitted. And our fine chemists and work on the molecules, they developed these molecules, not us, this is the work from another group, but you see that this is the visible spectrum means 380 to 780, around 700. So there is no absorption. Entirely the visible spectrum is transmitted. But beyond that, the NIR, 800, 900, 1000, this is absorbed. So it creates, absorption is there. Then, the exciton formation, exciton dissociation, charge generation. So these solar cells work very good with IR, but not with visible. So which means they're transparent, but they will generate electricity. Most important things are they have to be photostable and their stability should also be ensured. Another example from Hong Kong, I think. This is also the scene through the photovoltaic panel, which is also transparent. And in this case, they are using ZNO and MO3. The other one, it was a very, very thin, a very thin silver layer, only 8 nanometer. That is why it is transparent. And in this case, the top electrode is molybdenum trioxide, which is also transparent. You need to have a transparent electrode. Okay, if your material is not absorbing in the visible also, you will not be able to have a good transparent cell unless your electrode is also transparent. Now, smart flooring with mechanical energy harvesting. You are familiar with piezoelectric, when you apply pressure, certain materials generate electricity. So that is piezoelectric. Or you apply electricity, quartz, for example, they oscillate. So lack of inversion symmetry should be there. No, a lot of material properties are there, but I'm not going into that. But you understand this, that when you apply mechanical energy, you can create electrical energy. Same is true with triboelectric, but it is a contact electrification. So two dissimilar metals having two different work functions, they are bringing together, then there is a potential generated between them. To move them apart or you bring them close, then momentarily there will be a peak, as an electric field, which you can also harvest. You can charge a capacitor, a supercapacitor, for example. And that is where you can use smart flooring. Somebody is working, it will create some electricity. And in Germany or somewhere, a test case, some road is done with this. Vehicles are going, electricity will be created. Of course, initially very expensive, but we hope with the time this technology will also come down. Dr. Achyuchandran developed this insole. So inside the shoe, you have this. Somebody is walking, little bit of electrical energy can be created. This can be used to charge your mobile phone. That is the ultimate idea. So we offer flexible and rigid lead-free perovskite because piezoelectrics are there with the lead. We don't want to do that. The toxicity, lead toxicity, we try to avoid. And nano generators can be done, wearable nano generators, self-powered electronic devices, IoT-enabled device platforms, embedded electronics, medical device. So the possibilities are unimaginable. You bring the technology, probably you don't even know where the technology will be applied. But maybe in the next week, next month, next year, next decade, some applications will be there. This is where the lab level research and the actual frontier application will differ. The other one is waste heat harvesting using thermoelectric generators. Thermoelectricity, you know that when there is a temperature difference across a PN junction, it creates a thermo EMF. It can be used for when it is creating and when it is dissipating. Both ways you have this Seebeck effect and the Peltier effect. These things. But there are commercial thermoelectric generators. They are brittle, they are rigid, they are heavy. This is where CSIR and NIST are working on lightweight organic inorganic thermoelectric composite. We also develop P-type and N-type thermoelectric with polymer, graphene nanocomposite, polymer, metal oxide nanocomposites. And these interconnects are also very important when you connect between P and N, the kind of conductivity of the material, the printability, the durability. So flexible and rigid thermoelectric modules we can do, and large area testing, fabrication facility. Okay. Now, what is the application? You generate a flexible thermoelectric generator. What you will do with that? So think about a pipe, for example, from a factory. Hot effluents are going out. This is a waste heat. If you can recover some of the waste heat, this will add to the energy saving of the building because energy saved is energy generated. Similarly, energy generator will add to the energy credit of the building. So this is all PN junction connection. Okay. And this is the wound over the hot plate. So at these tips, you have a thermo EMF, which you can take it to the external circuit. And these are kind of low quality heat. Low quality in the sense 200 degrees Celsius. This is what we are attempting. So I believe to some extent, it can be used for flats and other places where some kind of waste management, incinerator, those things are there. Then those waste heat recovery is possible. Whatever you do here will be a bonus because otherwise it is going to be a waste. So with the government subsidies, of course, if we can do this, some of the energy requirements of the building can be met. With this, I am concluding the research frontiers of CSIR and NIST. Since this is more on sustainability, climate change, I thought I will spend some time on energy and climate change awareness program, which CSIR and NIST is continuously doing in schools and colleges with the support of Energy Swaraj Foundation. So this is a energy climate clock. Maybe you are aware of this climate clock. It is showing what? It is showing 4 years, 229 days, 3 minutes, 30 seconds, 3 hours, 30 minutes, and 0 seconds. What is this? This is a countdown clock. This is the time left to limit global warming to 1.5 degrees Celsius. The Paris Accord, right? In Paris Climate Accord, all the nations together took a pledge that we will bring down or control the global temperature rise to below 1.5 degree compared to pre-industrial level. The industrial revolution happened when? The time period. So 1900, 1850 to 1900. And that time, what was the global temperature? Above that, it should be 1.5 only. And this should be done within this time frame, 4 years. Every day, 1 day is coming down. And if you have a lot more efforts to control the emission, if you control the global energy resources and all, then you get more time. But you are not doing, then this clock will run faster. It's a dynamic clock. Okay. Professor Chetan Solanki is the person who is leading this activity, professor from IIT Bombay, and he is traveling across India spreading this message. We are also impressed by this effort. That is why CSR is part of that. We signed an MOU with Energy Swaraj Foundation. Okay. And if anybody wants to have a talk of Professor Chetan Solanki, we can arrange that. So there is a climate change. My question is, have you experienced a change in climate? Some people say there is no climate change. You ask Donald Trump, he was saying that there is no climate change, right? Last time when he was president, he was saying there is no climate change. So there are still people in the denial mode. They say that it is not there, it is not there, but it is there. Why I'm saying it is there? Look at the global average surface temperature. So the difference from 1901 to 2000 average, you consider and take it the difference, you put it at 0. Then you see that up to 1920, the difference was negative also. But beyond that, it is increasing. If you consider compared to the average between 1901 and 2000, from that average, our global temperature rise in 2020 is 1.2 degrees Celsius. Alarming. I would say it is alarming. And why it is alarming? These pictures are self-explanatory. I don't have to say what is happening here. Now, do you agree with me that there is a climate change? There is, definitely there is. So people like me, I repeat, who are 50 plus, 55 plus. And when we were going to schools, and at that time, your monsoon was in time, your summer was in time. There may be little bit variations here and there. But can we see that now? Where is our Idavapadi? We ask. Where is our, okay, all those things, now everything is changed. This is a manifestation of climate change. Some people say that it is not there, but it is there. Now, what about droughts? What about heat waves? What is a heat wave? A place like Trivandrum has an average temperature, but the temperature in Trivandrum stays for more than 5 days. It is much higher than the average temperature. Then we call there is a heat wave. That is a sort of a definition for heat wave. And how many days, how many heat waves across the globe? Think about it. See, 2010 we had 279, 2020 to 280. In between, some control was there, but 2019 there was 174, 201, like this. So radical changes are happening here. And uncontrolled fashion it is going, heat waves. So look at the picture of India. Maximum temperature on May 1. So already is something like 40, between 40 and 44. So most part of India is experiencing more than 40 and 44 degrees Celsius temperature, maximum temperature on this May 1. So is it good? Think about these wildfires happened in Australia, New Zealand, and melting glaciers in Arctic. All these things are results of climate change. Now think about global sea level. Global sea level, change in sea level compared to 1993, 2008. See, now I am not even going to 1901 and all. Compare the period 1993 to 2008 average. And then it is going up and up and up, this millimeter only. Okay, but it is rising. It is rising. So if it increases by another 1 centimeter, a lot of land and earth will be underwater. This is a situation which may arise. Most of our cities may submerge. This can happen if you don't control. And think about tropical cyclones in India. It's very funny to give names. You will give Fani, Amphan, Azani, Sitrang, Failin, Javad, Titli, Nivar, Nisarga. Very good names, right? But they are cyclones ultimately. They kill people. They destroy resources, infrastructure. So this is also a result of cyclones. So global warming is there, and that is bad. This much we agree. So global warming is the long-term heating of Earth's surface observed since the pre-industrial period due to human activities, primarily fossil fuel burning, which increases heat trapping, greenhouse gas levels on Earth's surface. You know what is greenhouse gas, right? Carbon dioxide is required. Without that, Earth would be very, very cold. But that envelope becomes thicker. It doesn't allow heat to escape. Then what happens? The average global temperature also increases. This is a big problem. And global warming, I showed the picture already. Temperature change in the last 50 years, if you look at it, unfortunately, the largest change is happening at this pole. And India, if you look at the change is somewhere around 1%. Change in Europe is more. Change in most part of Africa is more happens. So the way infrastructure is developing and the other parameters, the forest coverage, everything is coming into picture here. But this is the data. So why climate change? You ask me. Modern human life is driven by energy. Because quality of life, one of the indicator is what is the per capita expenditure of energy. Compared to US, it is very low in India even now. Over 80% of world's energy requirements are fulfilled through use of carbon-based fuels like coal, oil, and gas. These fuels are made out of carbon and used in the form of petrol, diesel, LPG, cement materials. These greenhouse gases are causing heating of the planet, which has changed the climate. Is there a plan B? There is no plan B. Control it. That is the only way we can survive. So who is responsible? Every use of energy, petrol, diesel, LPG, electricity, material. See, even when we brush our teeth, the manufacturing of toothpaste itself has given a lot of CO2. So whatever we do, that is there, but unavoidable, of course. Furniture, cement contributes to climate change. Every person, irrespective of whether he is from India, from America, from Europe, whether he is rich or poor, boy or girl, everybody contributes to global warming, alarming climate change also. So when to start climate corrective actions? It is not tomorrow, now, immediately. This is a very, very pensive picture, very important picture. Look at this sad polar bear sitting here because its last resort is also melting down. This picture should be in your mind when you go back today after this class. We must limit global warming to less than 1.5 degrees Celsius mark, ideally or maximum of 2%. Beyond this, climate change will become irreversible and corrective actions will be ineffective. More floods, more droughts, more forest fires, more heat waves, more troubles to humans will become a norm. Every day will be a new normal. That is actually happening now. Every day will be a new normal. Every monsoon, you see that the amount of water with certain places increases, certain places. For example, Cherrapunji. When we were in school, we were seeing that the place which is having the largest rainfall in India is Cherrapunji. And Cherrapunji in between became a very, very dry place. Drought happened. So it's now or never. Act now. What you can do? What can an individual do? Every individual is contributing to climate change. Therefore, every individual must take part in corrective actions. Responsible. Each individual should become fully aware of the dangers of climate change and then start taking actions immediately. Okay. So some actions everybody knows. Some actions maybe a little bit more awareness will be required. And I'm sure most of us know these things, but just for the sake of it, I do this. There is an energy literacy training given by Energy Swaraj Foundation. From the website that is given below, you can go to that. So first of all, the point is that you become energy sensitive. So you have to become energy sensitive. So how much I am using, how much I actually require. Think about what Mahatma Gandhi said. I again go to another quote. Earth has, the mother nature has everything for everyone's need, but not for everyone's greed. So this is an idea put forward by Professor Solanki to limit some of the requirements that can be done. It's not impossible. So how much energy is being used? You have to have an idea, particularly in your classes. Tell your students to do this exercise and ask them from where the energy is coming from. What is one person's carbon footprint? Very good exercise. One can do that. What are the impacts of energy use on the environment? What are the alternatives? What is the best approach for energy generation and consumption? Solar, people say it is there, but too much solar is also not good because to create solar panels, there's a very energy intensive process is there. We use energy in our daily life, and where do the energy come from? So primarily crude oil, coal is there, little bit of natural gas, cooking gas, wind, solar panel, thermoelectric. These are the sources of energy. And in this, now one should be able to make a distinction between renewable, non-renewable. And in renewable also, which is the energy efficient one, those kind of things one has to. So in short, capacity, category wise, all India, I can read how much it is. This much megawatt is there. But if you look at this graph, even now our energy, 31.22% from renewable energy sources. This is what is coming from 31.22. But other things, you look at coal, almost half of it, and then diesel, hydro, okay. But so this is the lifeline. World's energy from renewables at the moment is 14%. This is something we need to increase. See, for example, nuclear energy is a clean energy, but it is only 7,480 megawatt. Okay. Where the energy is used, where your energy is going, understand. Cooling and heating 58% for buildings, automotives, water heating 13%, lighting 10%, refrigeration 7%. Again, I am coming back to building technologies, cooking 6%, other appliances 6%. So we use a lot of energy in our daily life for manufacturing, packing, transportation, storage. So examples in our daily life that requires energy is to cook food, run a machine, brushing your teeth, to travel. Okay, how much energy do we use every day? An empirical calculation I can tell you. So this no need to tell you people, because you know what is the highest power of a bulb used at home. Nowadays it is energy efficient. Earlier it was not. Earlier incandescent lamps, as you know, it was a heat source rather than a light source. But our LEDs are actually very good energy efficient devices, because now we are using 15 watt. A 20 watt LED bulb is very bright, even brighter than a 100 watt incandescent lamp, right? So what is a unit? How much electricity used in a month? So these are units, what we call unit. Unit of energy is definitely power into time. So power is in watt and time in hour. So watt hour is the unit. And for ease, we say kilowatt hour. So let's calculate. 100 watt bulb works for 1 hour is 100 watt hour. 100 watt bulb works for 10 hours, 1000 watts. This is one unit. So now, can you ask your students to calculate the electricity energy requirement of their home? So interesting thing is that 1 unit is 1 kilowatt hour. You use energy for 1 kilowatt hour, considering all the processes, right from the energy generation, transmission, and conversion usage. You are using 1000 grams of CO2. This is an approximate calculation. Use 1, you have 1000 kilowatt, 1000 grams of carbon dioxide will be emitted. Now, our cooking gas cylinder, 1 LPG, 14 kilogram. 1 kilogram of LPG means 14 kilowatt hour energy. So 14 kilogram is 14 into 14 is 196, approximately 200 units. You know the 200 units. And 1 liter of diesel petrol, again, the calculation is 13 kilowatt hour, approximately. Now, when you bring 1 cylinder from the depot to your home, you know how much is spent on the transportation. And when you use that 1 cylinder, how much you are spending for cooking, all those things one can calculate. So countries' energy consumptions are not measured like this, because this is for a home. Since the quantity is less, one can do this. But tons of oil equivalent is a unit, and 1 ton is something like 11,630 kilowatt hour. 1 ton of crude oil, when you convert into energy terms, this is what. That's why big installations like a country, energy consumption is measured in TOE, which is tons of oil equivalent. One can calculate, very interesting exercise, how much is your carbon footprint that you can calculate. So carbon footprint comprises of emissions from, see, when you use crude, when you use burning something for, keeping your, in North India during winter season, you know that people are burning some wood, stick, something like that to heat them. So CO2 is generated, but you have the heat energy. So carbon footprint comprises of emissions from cooking gas, petrol, diesel, natural gas, electricity generation, construction, manufacturing of products, food production. So everything under the sun. Whatever you do, you will generate some carbon footprint. But have a balance. This is the message we've tried to give. Transport, there can be certain offsets because when you use the renewable energy sources and all, something we can manage. So when to start climate corrective actions? Already mentioned 1.5 degrees Celsius to 2 degrees Celsius and beyond. The climate change cannot be corrected. It becomes irreversible. So climate scientists warn us that we need to limit global warming to 1 point because it becomes irreversible. So this is where our climate clock is running faster and faster because we agreed that we will keep it below 1.5 degrees Celsius by 2030. But at this rate of increasing the global temperature, we have something like 4 hours or something. This is an old photo of a clock, but in the earlier picture I showed you, it is 4 years and something. That is what we have. 4 years, 229 days, 3 hours, 30 minutes. Climate clock is a clock that shows time left before certain global warming is reached. So we are making a clock. We can have the components from this. I suggest if you write to me, I can get you a climate clock from Energy Swaraj Foundation. To certain institutions, they even give it for free. Install it at your institution. Keep it as a, talking point. Keep it as a example, something which keeps on reminding you about climate change because it is not a joke. And keep it there in front of your institution, maybe in your library or maybe wherever, canteen. So it is a countdown clock which will keep on. We have done this. We put it in 3 schools in Trivandrum and at our institute also. And we are ready to supply a little bit more. And but in Kerala, probably we can go and do this. For other people, I suggest Energy Swaraj Foundation, you can write. They will be happy to provide. Okay, you can buy it online from Amazon. As I said, it is a reminder for us. I don't want to take more time for this. So there is a AMG rule, avoiding, minimizing, and generating the remaining 1/3 of energy. So avoid energy by 1/3, avoid usage of resources. You can't do that, but at least when you are coming, can you avoid using the lift? Then you are saving, definitely. Using efficient appliances, like I said, the incandescent lamp. Fortunately, not many people are using it. But AC, when you want to install an AC, can you buy a 5-star rating? Because energy efficiency will be high. That is required. And then generate, avoid 1/3, minimize usage by 1/3, generate by 1/3 using solar energy or whatever. So these are the important things one can do at home. Again, this is a talk about building technology. So use green technology wherever possible. Make your home smart. When not required, when no movement at room, keep your light switched off. There can be sensors. Utilize home assistants for cleaning and all. Energy star devices, I've already mentioned 5-star. Solar-based energy options, good energy rating. Look out for SEER ratings, which is seasonal energy efficiency ratio between this summer, winter, and all those. Energy saving power strips, energy saving mode for AC particularly, frequent inspections, what is happening, use dehumidifier because it will take more energy to cool down a room where humidity is high. Adjust the thermostat, maybe keep it at 26, 27. Change filters regularly, install ductless heat pumps, use an app to track energy usage. Okay, use of HVAC systems, ventilation, use fans, use energy efficient appliances, perform energy audits. This is something you can ask your students to do. They can actually do. As an assignment, you can say an energy audit. What is the total energy expenditure in your house for a month? And wherever you can save something, you can ask as an assignment or something. And plug of chargers, very, very important. plug of chargers. Most of us keep our mobile phone charger connected always. We believe that when the load is not connected, nothing happens. But read it, you will understand that a little bit of energy is dissipated always. And think about how many mobile phones may be there in India, or for that matter in the world. Even it is a very, very minuscule amount of energy, having millions and millions, crores and crores of mobile phones kept chargers kept connected will definitely be dissipate energy in a considerable rate, no doubt about that. Okay. So heating, ventilation, air conditioning systems, as much as possible, HVAC systems, as much as possible, try to reduce. So I think we are coming to the end of this. Take this pledge. I pledge to stop using air conditioner. Will be difficult, but not always. Huh?